Question is, a solutions architect is designing the data storage and retrieval architecture for a new application that a company will be launching soon. The application is designed to ingest millions of small records per minute from devices all around the world. Each record is less than 4 KB in size and needs to be stored in a durable location where it can be retrieved with low latency. The data is ephemeral and the company is required to store the data for 120 days only, after which the data can be deleted. The solutions architect calculates that during the course of a year, the storage requirements would be about 10 to 15 TB. Which storage strategy is the most cost effective and meets the design requirements? Option A. Design the application to store each incoming record as a single .csv file in an Amazon S3 bucket to allow for indexed retrieval. Configure a lifecycle policy to delete data older than 120 days. Option B. Design the application to store each incoming record in an Amazon DynamoDB table properly configured for the scale. Configure the DynamoDB time to leave TTL feature to delete records older than 120 days. Option C. Design the application to store each incoming record in a single table in an Amazon RDS MySQL database. Run a nightly cron job that executes a query to delete any records older than 120 days. Option D. Design the application to batch incoming records before writing them to an Amazon S3 bucket. Update the metadata for the object to contain the list of records in the batch and use the Amazon S3 metadata search feature to retrieve the data. Configure a lifecycle policy to delete the data after 120 days. Correct answer is option B. Design the application to store each incoming record in an Amazon DynamoDB table properly configured for the scale. Configure the DynamoDB time to live TTL feature to delete records older than 120 days. Next question is, a solutions architect is designing a network for a new cloud deployment. Each account will need autonomy to modify route tables and make changes. Centralized and controlled egress internet connectivity is also needed. The cloud footprint is expected to grow to thousands of AWS accounts. Which architecture will meet these requirements? Option A. A centralized transit VPC with a VPN connection to a standalone VPC in each account. Outbound internet traffic will be controlled by firewall appliances. Option B. A centralized shared VPC with a subnet for each account. Outbound internet traffic will be controlled through a fleet of proxy servers. Option C. A shared services VPC to host central assets to include a fleet of firewalls with a route to the internet. Each spoke VPC will peer to the central VPC. Option D. A shared transit gateway to which each VPC will be attached. Outbound internet access will route through a fleet of VPN-attached firewalls. Correct answer is option D. A shared transit gateway to each VPC will be attached. Outbound internet access will route through a fleet of VPN-attached firewalls. Next question is, a solutions architect is responsible for or redesigning a legacy Java applications to improve its availability, data durability, and scalability. Currently, the application runs on a single high-memory Amazon EC2 instance. It accepts HTTP requests from upstream clients, adds them to an in-memory queue, and responds with a 200 status. A separate application thread reads items from the queue, processes them, and persists the results to an Amazon RDS MySQL instance. The processing time for each item takes 90 seconds on average. most of which is spent waiting on external service calls. But the application is written to process multiple items in parallel. Traffic to this service is unpredictable. During period of high load, items may sit in the internal queue for over an hour while the application processes the backlog. In addition, the current system has issues with availability and data loss if the single application node fails. Clients that access this service cannot be modified. They expect to receive a response to each HTTP request they send within 10 seconds before they will time out and retry the request, which approach would improve the availability and durability of the system while decreasing the processing latency and minimizing costs. And the options are: option A, create an Amazon API Gateway REST API that uses Lambda proxy integration to pass requests to an AWS Lambda function. Migrate the core processing code to a Lambda function and write a wrapper class that provides a handler method that converts the proxy events to the internal application data model and invokes the processing module. Option B, create an Amazon API Gateway REST API that uses a service proxy to put item into an Amazon SOS queue. Extract the core processing code from the existing application and update it to pull items from Amazon SOS instead of an in-memory queue. Deploy the new processing application to smaller EC2 instances within an auto-scaling group that scales dynamically based on the approximately number of messages in the Amazon SOS queue. Option C, modify the application to use Amazon DynamoDB instead of Amazon RDS. Configure auto-scaling for the Amazon DynamoDB table. Deploy the application within an auto-scaling group with a scaling policy based on CPU utilization. Back the in-memory queue with a memory mapped file to an instance store volume and periodically write that file to Amazon S3. Option D, update the application to use a Redis task queue instead of the in-memory queue. Build a Docker container image for the application. Create an Amazon ECS task definition that includes the application container and a separate container to host Redis. Deploy the new task definition as an ECS service using AWS Fargate and enable auto-scaling. Correct answer is option B. Create an Amazon API Gateway REST API that uses a service proxy to put items in an Amazon SOS queue. Extract the core processing code from the existing application and update it to pull items from Amazon SOS instead of an in-memory queue. Deploy the new processing application to smaller EC2 instances within an auto-scaling group that scales dynamically based on the approximate number of messages in the Amazon SOS queue.